And so today's lecture is going to be on essentially wrapping up where I left off last time. So I'm going to be talking about inductive definitions. So last time we left off at a very boring point, I would say. We kind of started talking about grammars. We talked about how grammars are converted into Scala. And I hope you had an opportunity to get to the recitation where they did more examples of the grammar of set with intersection, unions, and so on, and converted that into Scala. So you have some experience doing that. So today I'm going to show you a few more examples of grammars that are naturally written down as inductive definitions. Once we do that, I would like to go ahead and talk about how do you work with inductive definitions. Okay, so the agenda for today is first I will talk briefly about the grammar of trees. Then from there, we'll talk about the grammar of expressions, and then from there, the grammar of programs. Everything I'm going to talk about is based on two notebooks. So the notebook from last week on inductively defined structure is going to be continuing as the notebook for this week. So I have not covered certain things like lists. So I hope you have the time to look into lists as well. I will start with trees today, and then I'll go from there. All right. So I wanted to define trees today as an inductive data structure. All right. So what is a tree? Well, ideally, a tree is a structure that looks like this. So you have a node, and particularly, I'm looking at binary trees. So every node has two children, a left child and a right child. And every node also has a number that's associated with it. That's the data associated with every node. And you also have leaves, which I'm just calling leaves. All right, so here is another example. The node 4, left child is 8, right child is 9, left child is leaf, the right child of 9 is 4, again, and leaf and leaf. So this is not a binary search tree. This is just a regular binary tree without any constraints. So far, okay, so far so good. Okay, so I hope so. So how do you write this tree as a grammar? So I've already done that here. So I'm just going to copy this over so that you don't have to do this again. So I'll copy this over to my lecture notebook and just walk you through this grammar. All right, so what's this grammar? So let me actually make it into a slightly more readable grammar. All right, so the grammar has one non-terminal called num tree and a non-terminal called num. And a num tree is a tree with numbers. And a num tree can be a leaf. So one of the constructors in the grammar, or one of the terminal symbols, is a leaf. And another terminal symbol is a symbol called node, which takes in 3 arguments: a number, a num tree, and a num tree. Okay, so this is going to be the grammar that we are going to work with. So these are the rules. And numbers are, by the way, natural numbers. So they can be simply 0, 1, 2, 3, all the way to infinity. And this is, you can think of this as either infinitely many rules, or we have a shortcut. There is a data type in Scala for numbers, which is the integer data type. So I'm simply going to use the integer data type interchangeably for now, and just cheat that way. Even though integer allows negative numbers, I'll just use that and cheat. The alternative is you can use the numbers with 0 and successor that I talked about last lecture, but that's not going to look very pretty. We could try that as part of this lecture. Okay, so hope everyone's with me so far. All right, so if there are no questions, let's take a second to convert this grammar into Scala. All right, and how do you convert this grammar into Scala? Well, the way you convert this grammar into Scala is like this. So remember, every non-terminal that you want to encode has to have a sealed trait. So I would write sealed trait num tree. Okay, and since I'm going to identify numbers with the inbuilt type of integers already in Scala, I am not going to write sealed trait num. You could write type num equals int, if you will. I mean, if you want to be that specific, you could do that. you could just say num is an alias for the type int, because I'm going to identify num with the type int in Scala. So hopefully this is good. Hopefully this doesn't confuse anyone. Now, each of these definitions will need to be a case class. So I would say case class leaf, and leaf has no parameters, extends, and this is where the left-hand side of the rule comes in, num tree. All right. And then I would say case class for this rule, the rule that I'm highlighting, case class node. Node has 3 arguments, argument n called num. Then the second argument is of type num tree. So I'm going to call it left because it means something to me. And then the third argument is a num tree. So I'm going to call right, extends, num tree. Okay, so there is a nice question here. Leaf could be a case object too, right? Yes, absolutely. And the reason you would write leaf as a case object is I really don't feel like writing empty open brackets, close brackets. So I was hoping someone would point out, and you did. Thank you so much. Kudos. Hopefully this is good, right? And I'm not going to write anything for num. So all these rules here are just telling me to identify num with an inbuilt data type and move on. Okay, so this is a definition for a tree. Okay, and now I can identify various trees with terms in this language, right? In this definition. So as an example, the tree with node 4, node 8, leaf, leaf, node 9, leaf, node 4, leaf, leaf is this tree. Okay, how do you figure that out? So look at this part, node 4, leaf, leaf is this part of the tree, the part of the tree with 4 and leaf as the left child and leaf as the right child. This part, the highlighted part, node 9, leaf, node 4, leaf, leaf is this one. It's a node with 9 in it. Its left child is a leaf, and the right child is a node with 4 and 2 leaves. So you can see how this entire, okay, so let's take this part. Node 8, leaf, leaf is this subtree, 8 with a leaf and a leaf. And the whole thing, node 4, node 8, leaf, so this whole mess is this entire tree. So you can now represent a tree in terms of an inductive data type. So I can say val t1 is node 4, leaf, leaf. And I can say val t2 is node 8, leaf, t1. Okay, so you can start writing more and more complicated definition. Val t3 is node 10, t1, t2, so on. Okay, so there's a question. Should we think about figuring out the way to construct these as the same way to approach the chain rule in calculus by identifying the innermost function first? Yeah, I would say yes, but it's not as complicated as a chain rule in calculus. The way to construct this is almost bottom up. Yes, you would, if you go back to this example, you would construct like a little subtree here with 4, and then you would construct a bigger tree, and then you would construct this subtree, and then you would construct the entire thing. One thing to be said here is, as a user, you're never expected to write things this way. And that's something I'm going to have to talk about. And that's, we'll come to that in a bit. You are never expected to write things this way. You're never expected to say node 4, node 8, leaf, leaf, leaf. This is just a way of identifying trees. Now, how do you build up trees and so on is, we need to talk about that. Okay, so I'm like deliberately holding things back and not getting there. But I hope this is okay. I don't want to belabor this point, but I hope you can see how I have defined a way like a binary tree-like data structure as inductive definition. There's nothing more until I tell you what can we do with this, right? So I'm going to talk about what can we do with this in a second. All right, so let me move forward and talk about a more complicated grammar, okay? So let me talk about a more complicated grammar, which is going to be a grammar of arithmetic operators. So now that we have defined trees, we can now define something more complicated. Okay, This is a grammar of arithmetic expressions. All right. So how does this go? So here in this grammar, the non-terminals include expression, expr, which is an expression. Uh, you have this non-terminal called double. I'm going to identify double with the data type of the same name in Scala. So I'm not going to keep this double around. I'm just going to identify it with Scala, but technically it's a non-terminal. Then you have a constructor that says it's an ident of an identifier. Okay, and so in this course, when I talk about identifier, what I mean is the name of a variable. I don't like to call them variables because sometimes they can be a val instead of a var. So I would like to just call them identifier. Okay, and I'm going to match identifier with string, the string data type in Scala. Okay, then comes interesting. So then comes plus of two expressions. So plus is a constructor which has two arguments, which are the two things that you are hopefully going to add up. Okay, for example, minus is a constructor that's going to talk about subtracting two things. Mult is a constructor for multiplication of two expressions. Div is a constructor for dividing two expressions. And then I've gone crazy because I love calculus, and I wrote down log, exp, sine, and cosine as some unary operators. Okay, and remember, technically double is a non-terminal in my grammar, but I'm secretly going to identify it with all double precision numbers. But still, I just tell you that it's identified with all double precision numbers somehow. And identifiers are going to be strings. In this case, I am a little bit particular. This is a regular expression that says it's all strings that start either with a small letter from A to Z or a capital letter from A to Z, followed by arbitrarily many occurrences of A to Z alphabets, numbers, the underscore, and the star is the Kleene star. So this is regular expression syntax. So I can be very specific in talking about identifiers, or I can simply say any string is an identifier, and an identifier is just identified with the Scala type string. Okay, so let me copy this definition over. And let's take a second to maybe express this definition in Scala. Okay, so this is an example of a grammar that's going to do something useful for us. It's going to help us talk about arithmetic expressions. All right, and a week from now, this is the grammar we are going to start to write our first interpreter. So when we talk about interpreter, this is the grammar that we are going to bother interpreting. All right, so here's the grammar. Okay, so how do you express this grammar in Scala? So you would have to write sealed trait expr to define the non-terminal expr. All right, and then I'm not going to worry about double. So I would love to say type double equals double, but that's not needed. I'm going to identify double with the Scala double, and I'm going to cheat and identify the non-terminal identifier with Scala string. So instead of making a big to-do about not everything being an identifier, I'm just simply going to say any string is an identifier for me. Okay, so now I can start to write the Scala definition. So I can say, so this definition, so let's look at this rule. Expression gives const double. So this rule is written out as, so expression yields a const with a double. So this is written out as case class const with an argument double, d colon double, extends expr. Okay, so what's the purpose of creating a new type instead of just using string or int in these examples? There is no purpose at all. I just wanted to show you that I am identifying. So because I wrote it as an identifier in the grammar, I'm just writing this type declaration here. It's not needed, right? So this is like this is not needed. This is just me telling you that I am doing this so that when you look at this notebook later on, you're not confused. You know, he talked about identifier and it's just vanished and become strings. What happened there? This is just me telling you that this is what I'm doing. Okay. All right. I hope it's okay. So let's do this rule. So how about expression gives ident, that's the name of the constructor, identifier. So can someone type in the chat window, well, how would I write this out in Scala? Okay, so someone's really fast here. Very good. Okay, case class ident, used a capital I, perfect. I, S, whatever you want to call it, extends exp. Okay, so I'm going to be, I mean, it's going to be boring if I walk you through everything. So I'm just going to walk you through a few things. Let's do expression gives. So someone else, please help me with this. Expression is a plus of two expressions. Someone other than Ryan. Case class plus E1 expression, E2 expression extends EXPR. Perfect. Only nitpick is Scala doesn't like you to do capital letters for identifier names. So in Scala, you might want to just use small letters. Now, of course, let's just do the capital letters so that we see what Scala tells us. So it doesn't complain too much, but it's a good convention here if you just used small letters. If you started every identifier with a small letter, because typically in Scala, like convention, capital letters are type names. Perfect, perfect. Thank you. Very good, very good. Same for minus, same for multiplication, same for div. It's just going to change this plus to a minus mult div, right? Okay, so there is a question here. Can you explain what a sealed trait is one more time? All right. So the idea behind a sealed trait is let's start with the simple thing, the trait. The sealed is just me being a little bit more fancier than I need to be. Let's start with a trait. A trait in Scala is an abstract class. So it's a class whose, I don't need to define it. I don't need to, I just need to declare it and tell you that something called EXPR exists. So once I declare this, then everything can inherit from EXPR. Okay, so this is a way for me to write down this grammar as an inductive type. And to be able to write down this grammar as an inductive type, the way I do it in Scala is I overload the inheritance mechanism in Scala. So I define a parent class or a the parent of all classes, and I call it EXPR. And everything is going to overload from EXPR to be able to define things. Okay, and so that's why it's a trait. And the reason it's sealed is because I want to tell Scala that all the things that are going to extend it are in the same file. And to say that, you say it's sealed. Okay, that's just a Scala thing. You can get away without saying it, but saying it is better. Okay, so there is another question. So the question is, so we don't set ident s:string because we set identifier to string. Would it work if you just did this? If I just called it string, it would just work. And the reason is, so sorry, let me just do this. So the reason it would just work is it's just saying identifier and string are the same things. Okay, so it's just a type def or a type alias. In C, you would have done something like type def, my string, const car star, maybe the opposite way. But you're allowed to call a type by a different name, right? It's the same thing that you do in Scala. I'm just simply saying identifier is the name of a type, and it means the same thing as a Scala string. Okay, good question. Very good. So so it's const is const d:double. That's right. Because in the grammar, I define const as a double, and I just identify this double with the Scala type double. Okay. And I use capitals because Scala doesn't like it if I called a class with a small. It does like it. I mean, so these are just conventions. Okay, sorry, I didn't. I was under the impression that you can't do it. Apparently, you can do it, But the convention that I have held for a long time is I always keep class names and type names capital letters and identifier names small letters. It's just I'm somewhat old school that way, but I think most Scala programmers do that too. There are these unspoken conventions people use. It's not written in stone. When I said it was written in stone, I misspoke. But typically keep the capital letters for class names and keep the small letters for type names. Sorry, for variable names. Okay, I think everyone's good. Okay, questions have settled down. All right, very good. So we did minus. So let's just do one more, plus, minus. Let's do multiplication and log. So how would you do multiplication? So you do multiplication exactly the same way as minus, case class mult, e1 colon expr, e2 colon expr, extends expr. Case class log, e colon expr, extends expr. Okay. Now, what good is this, right? What good is this kind of a language, right? This kind of a definition. So suppose I wanted to write the function log x times y plus, x minus, let's do 2y. So I wanted to do something fancy like this. Okay, so I wanted to do a log x times y plus x minus 2y. How would I write this down in this definition? How would I represent this function? So I would say val v1. So let me do things like this. So val x is identifier of x. Val y is ident of y. So this is just the variable, just the identifier x. This is just the identifier y. All right. Now let's do x times y. So val xy is mult of x of y. So this gives you mult of ident of x of ident of y. So this would be, so this is represents x times y. Okay. So you can now see how complicated expressions are being built up from simple expressions. Then you can say val x minus 2y equals minus of ident of x, comma, mult of const of 2, comma, ident of y. So this is the complicated thing, is x minus 2y. Okay, and then you say val e equals log of xy plus of xy xm to y. So this monstrosity here is the definition of this function written out like this. Okay, now you might say, what use is writing things down like this? And to that, I would say be patient. The users are coming up in a second, and the entire rest of this class is going to use this mechanism to define an entire programming language. Okay, very good. So there is a nice question here. Is there any reason to keep using the ident rather than x and y we have created? Absolutely no reason. I just wanted to show you that you can, this x and this y are just going to stand for ident of x and ident of y. The reason I wrote this is to make life easier, right? So you wouldn't want to do this. You would want to do this. So let me just call this vx and vy so that people aren't confused here. And then you would simply write things in a much nicer format. Okay, vy. And then let me call this 2. And then I could say val 2 equals const of 2.0. Okay, so this is how I'm building up complicated expressions. And by the way, this is almost getting to be like a domain specific language that I've defined to help me write out functions. Why would I want to write out functions like this? There are plenty of uses. One example that's like this example on steroids would be TensorFlow. If you ever heard of TensorFlow, TensorFlow is just a domain-specific language that allows you to write definitions like this, and it becomes something called a computation graph. Okay, so you can write down complicated functions which are just machine learning models, and what you get is a graph. It's a graph, and it's called a computation graph. And you can think of this as a very simple way of writing functions. Uh, and this is a way you start building up a domain specific language. So I built a little domain specific language, or a DSL, for helping you write down expressions, arithmetic expressions. Okay, now the cool thing comes in, because I can do some cool things. So in a few minutes I will show you how to work with these arithmetic expressions, right? So we'll show you that. Good so far? Okay, hopefully good. All right, so let's move forward, and let me get to the last part of this, right? So the last part of this is I wanted to talk about how this becomes so powerful that you can now start to write entire programs this way. So I wanted to define a language called Mython, which is a play on Python, right? So my Python. So I wanted to define a language called Mython. So I did it like this. So after I defined arithmetic expressions, so remember this grammar called EXPR, which we just defined. It's the grammar of arithmetic expressions. Let me define a grammar on top of it. And this grammar is going to be the grammar of conditional expressions. So things that evaluate to true or false. How do conditional expressions get built up? From arithmetic expressions. And the idea here is very simple. I say a conditional expression is a constant which is a true, or a constant which is a false. All right. Or a conditional expression is greater than equal to applied to two expressions. So it's read it as E1 greater than equal to E2 is written in this form like this, or it's less than equal to of two expressions, or it's equal to, like the equality of two expressions, or, and remember these expressions are what kind of expressions? This EXPR expressions are what kind of expressions are they? They are non-terminals, but they are non-terminals from a different grammar that I already done before. Perfect, right? See, these are basically referring back to a grammar that I have already defined before. So you have to tack this grammar on. So these are arithmetic expressions, right? It makes no sense to say conditional expression is greater than conditional expression, right? Or you can say that in C, but it generally doesn't make sense to say that. All right, now comes AND. Notice the difference here. AND is the AND operator, but it's AND of two conditional expressions. OR is the OR of two conditional expressions, things that give you Boolean, and NOT is the NOT of a conditional expression. So this entire thing, when tacked on to expressions, now gives us basic arithmetic, and it gives us all the comparison operators, and it gives us AND and OR on top of it. Good so far? So now I'm building up towards this language called Mython, right? So I'm building up towards this language called Mython. So and Mython is remember my plus Python, right? It's my version of Python so far. Very impoverished, but still it's a version of Python. And so you can write conditional expressions in Scala. Is this okay? So this shouldn't be very surprising. This is just a simple exercise in translating this grammar into this set of definitions down here.